Welcome to Chapter 12, still talking about sound, and this is Section 1, Part B. We're going to talk about something called the Doppler Effect. So our goal in this section is we're going to learn and to recognize what the Doppler Effect is and when we are experiencing it. And we're also going to determine the direction of a frequency shift when there is relative motion between a source and an observer. So the first thing we need to do is learn a new word, and this is the word propagation. So when we talk about wave propagation, this is the word used to describe the way a wave moves through a medium. So for example, if we look at this tuning fork here, okay, if we ping it, the waves will move out in all these different directions through the air. Just the fact that those waves will do that is what we call propagation. Waves propagate. And it's important to notice that sound waves propagate in 3 dimensions, meaning they go this way, but they also go, like we could imagine, into it or out of towards us. Basically, waves go in all directions, or sound waves do. So the other thing I want to point out here and remind you is how we turn a longitudinal wave into a graph, because that's going to help us understand the next step of what we're looking at. So if I were to take my pen, okay, and if we were to draw, you can see here's an area where they're more dense. Here's another area of denseness, another area of denseness. And remember, when we turn this into a graph that looks like a transverse wave, but it's of a longitudinal wave, these areas of denseness are the peaks, right? So we could kind of just draw a line up here, and so we know a peak's going to be there, a peak's going to be there, and a peak's going to be there. Okay, and then we know that troughs are going to be these areas of less dense, so that will fall in between all of these, and even right at the source right now. So now if I imagine that this is my equilibrium point, and I draw my graph of what this will look like, okay, then essentially what's happening is I have a graph that is doing this. Okay, so all my peaks, and it's not a perfect graph, but all my peaks roughly line up with those pink dots. Okay. So what we call each of these peaks here then, when we draw it like this, we could also draw these as a line. So you see how they represent lines? We have these lines going out. So there's one line, there's the other, there's another. Okay, so these tops of these peaks, we call these wave fronts. And they just let us know that waves are passing by, and we draw them as circles and single lines going out from some source. So now we can get into what the Doppler effect is. So I want you to think, and have you ever noticed how an ambulance or any sort of vehicle with a siren coming towards you sounds higher, it has a higher pitch, than an ambulance or other vehicle with a siren going away from you? Now, if you've never noticed this, go ahead and try to notice it the next time, because this is something that always happens. And this fact that this happens and that you can observe this is the Doppler effect. Okay, so what causes it? We know what happens now, so what makes it happen? Well, what happens is, you can imagine this is the vehicle coming towards you. And if you look from the vehicle's point of view, right, if you're inside a car, you know, you are stationary compared to the car around you, right? And then, but if somebody is outside, you see everything going past you, right? So if the car is driving forward, it looks like the trees and the buildings, they're going backwards past you. But to an observer, right, you're coming towards them and you move past them. So this is what is called relative motion. Okay. And when this happens, if something is emitting sound, okay, so we have this vehicle, an ambulance, that's giving off a sound. And this is what the sound looks like coming off of it. It's just this wave, okay, and it's going equally in all directions. But the air around it is not moving. And so what happens is, as it is moving forward, okay, it gives off one of the beats of a siren, right? And then it gives off another. And during that time, it has moved forward. So it's actually kind of like catching up and getting closer to the sound it just gave off. And so as it continues, what it does is it forces the sound waves in front of it to be closer together, and the sound waves behind it, because they're moving away from the sound that it's giving, to be further apart. So each of these little circles represents a wave front, like we were just talking about. And so if we draw these now as waves instead, okay, These waves here are the source of it coming towards you, so it'd be this part of the wave here. Okay, so they end up being closer together than in the stationary version. And then the other part of the waves here, where it's further apart, would look like this. Okay, and that's what it sounds like as it's moving away. So if a siren, and this is opposite, okay, the car comes around and he comes this way, right? He comes closer as he's coming towards you. The pitch sounds higher because the frequency is higher. And then as it passes you and keeps going, then the frequency gets spread out. The frequency is less, it's lower, and so it sounds lower. And this is the Doppler effect. Now, I want you to pause here and watch this video, especially if you've never noticed effect. Okay, the link is below right here. You can copy it down. And it's also in the description or in your Chapter 12 Schoology folder. But it just goes through this while actually showing an example of the Doppler effect. So the last thing I want to show you, excuse me, not quite the last thing, but close, is you should always be able to tell the direction something is moving based on a picture like this of the Doppler effect. Okay? So we know that as it's going towards something, the sound waves will get closer together. So if we had to draw a person, right, where is our person standing, okay, if this is the picture that they're seeing? Well, it has to be closer, and the area where the waves are the closest is right here. Okay, so that means our person must be standing over here. And not only that, but that means that this object is traveling in that direction towards them. Okay, if the person were standing over here, okay, then they would hear a lower pitched frequency. So here this person hears a low pitched frequency, and here this person hears a high pitched frequency. Okay, and this object is moving in this direction here, because these are spaced so closely together. So a fun fact of the Doppler effect is something I want to show you here, because it's a really interesting application of this. Okay, and it's called what we know as the sound barrier. So sound travels at a specific speed, and we've mentioned in a couple problems that it's anywhere between 331 to 340 meters per second. Okay, and that translates to 1,126 kilometers per hour. So if we think about waves in a pond instead of sound waves for a minute, okay, and that's what this is a picture of. Okay, if we throw a pebble in a pond, the waves radiate out like this. A boat moving will also give off waves, and it has the Doppler effect also, though we don't see it as readily. So if you imagine the front of the boat, right, it gives off these waves as it moves, and as it moves forward, it passes through the waves that it gives off. So if the boat were to move really slowly, we could kind of see each of these waves being given off in this kind of pattern. And what happens, though, is most boats go so fast that you just get something like this, that in English we call a wake. And it's just a wave that kind of turns into one wave that you see given off. And it's a combination of all of these. You can even kind of see it being created a little bit here by just this effect that you get. This is the most visible part. These waves still exist, but this is the one you really see. So as the boat travels faster, the wake gets more narrow and closer to the boat. So it turns out that in a boat, this always happens because the boat easily goes so much faster than the wave would propagate on its own. But sound is so fast, it's hard to go faster than the speed of sound. But if you do this, okay, like if we take a fighter jet like the one you can see right here, okay, fighter jets have to go faster than this, and they too can break the sound barrier. Okay, and to break the sound barrier means they are going faster than the speed of sound, and they essentially create a wake in the air. And when they do this, you can actually see the wake, because remember, sound waves are longitudinal, and so there's this pressure, okay, and you can actually see the pressure. It's visible when a fighter jet passes the sound barrier. And so that's just kind of a fun little cool thing that has to do with the Doppler effect and what we have been learning. So please go ahead and ask me any questions you have in class, and that is the end of section 1 of chapter 12 on sound. See you guys in class.